Swayam Prabha. Digital India. Educated India.
Let's talk a little bit about supply chain. This is perfect following Dr. Chetty, because it's now we're talking about supply chain, right? It's something which we have kind of ignored. We've ignored that there is a need to do things in a timely manner for a successful operation. So we'll look at what all do we need, what all needs to happen so that we have successful CCS operation. If we get time, we will talk a little bit about another way to transport, and that is transporting carbon dioxide as a natural gas, solid natural gas, that's what we call it. It means as a hydrate form. But for now, let's look at what the supply chain challenges are. This is going to be a very dry thing, so I hope you give me more information back so that we can populate this with more information. Especially, I'm looking at all of the folks who are in industry who are trying to do this as a living. So we'll have two parts to this again. We'll have a little bit on transport, pipelines, what do we need, but then a lot more on something really I find it exciting, and that is to transport carbon dioxide or methane as a gas hydrate. But that for future. So what do we need? What do we have, right? So first of all, we need money. In everything that we do, we need money. We have to have money, and that money is anyway. So what we need is some upfront costs. We need to build infrastructure. We need to drill a well. We need to do all the a priori work. We need to have the storage facility. We need to have transportation. All of that requires subsidies, requires pricing, and requires other incentives. It requires investments from companies, and so there is a very high cost of capture, and there is a high cost of infrastructure. So all of that requires significant capital investment upfront. The part that is very difficult to manage is when it is very inconsistent. So for example, you have government change, and we're going through that right now. There is a change in the government, and investments are then held back to wait to see if the policy might change. If the policy changes, all of that investment that has been promised dries up. So we're running into that problem for our project. We have a commercial partner that is a startup, and they have pledged to put in $8 million from their own funding. At the time when we wrote the proposal 2 years ago, things were looking really strong for CCS. Everyone was developing new projects. There were oil companies that were very much interested to invest. They were going green. There was the whole thing of British Petroleum, what used to be British Petroleum, changing its name to Beyond Petroleum, and now to just plain BP. And at some point they realized we cannot be green because we are still producing oil and gas, and that is going to be our main revenue. So that went away. Exxon, same way. Exxon wanted to declare itself to be a non-oil and gas company. And then they realized their shareholders are screaming and pulling out and saying, no, you will not be a non-oil and gas company. So Exxon has gone the other way. Chevron had very big campaign to call itself the human energy company, where their main capital is their humans, that means their workforce. Those ads have been pulled. And so there is a change in the sentiment. There is a change in the sentiment and the appetite for investment because of potential anticipated incentives change, because of anticipated policy change. So that becomes a real stumbling block, because the economic viability of projects now is not guaranteed. And so when we talk about supply chain, at the very beginning, we need to have the money guaranteed. If there is no money guaranteed, nothing works. And so if we are looking at the challenges, the economy, it can be changing or it can be confusing policies. They can break storage projects. And so that's a real threat. So if you're doing a SWOT analysis of every project, which you would need to do before you start, in the SWOT analysis, economics will be a big major threat. Okay. Together with that, we have regulatory hurdles. You have certain type of regulations that guide and define everything we do. Right? In the US, we have Class 6 well permits. We have guidelines on what to put in the well, what type of material, how to build the well, how to manage and store carbon dioxide. What are the regulations following that? What are the a priori information? How much emissions are allowed? For example, I'll give you a very practical example. There is a regulation of not allowing CCS projects in formations that have lower than 10,000 parts per million of total dissolved solids. Now that becomes a hurdle, because 10,000 parts per million is much too high for any drinking water. And so if there is a regulatory policy that doesn't have a big relevance to the type of safety it is regulating, that makes then a huge hurdle. That 10,000 parts per million is a definite threat to my project, because we think we will be right around 9,600 to 10,000 ppm, which means that the major formation that we are trying to target might not be available. Right? So that becomes a impediment. It can also be a delay. So there might be some part of a guideline. For us, it is the guideline to prove that there are no ancient artifacts in the region. For all practical purposes, there might not be, but the proof lies on the project, which means that is an additional implementation requirement that causes a delay. All of these increases the uncertainty for investors. So investors need to have a certain appetite, right? As the risk increases, as regulatory standards get more stringent, if they are explainable, it's good. That's required. No question about that. If they are not explainable, if you're on the borderline, that's when things get a little dicey, and that's when you start coming into challenges. If we are transporting carbon dioxide across states or across countries, for example, we investigated the Weyburn project that is located in Canada, but is importing carbon dioxide from Beulah in Montana. You're crossing not only state, but you're crossing country boundaries. So if there are different regulations on how to safely transport carbon dioxide, then you have to adhere to the more stringent requirement. And so your project suddenly has additional cost. You might be cited, the project might be cited in one state which has better regulation. But if you're sourcing your carbon dioxide from a state with higher, more strict regulations, then you have to make your project, you have to scope your project to the more stringent requirement, because that manages the overall requirement for you. Regulatory complexity. If no one understands what the regulation is, there is then a secondary market that comes into play of people who can read the government's intention and interpret the regulations that are way too complex for every normal project. And so that makes it a big challenge. There is another thing which is, I don't know what the scenario is here in India, but there is a public acceptance challenge. In the US, there is a big challenge. People do not want this in their communities. This was the example we started with on day one, to say, if I were to get permission to drill a well on the football field here, how would you feel? Right? So that's the part which is a challenge, where there are communities saying not in my backyard, and there are interest groups saying not in anyone's backyard. It doesn't matter where you put it, it doesn't need to happen. And so there are concerns. There are real concerns that are about environmental impacts, but there are also concerns about requiring unrealistic expectations. The part which is really interesting here is when we look at risk, there is a risk of there is a known risk, right? It's a known risk to geologists. If you do carbon storage, there will be a risk at 0.005%. I'm just pulling numbers, right? 0.5% risk. As a geologist, that is non-existent. As a non-geologist, that is a risk, and I don't care what it is there. Right? It's like going to a doctor and the doctor tells you you have a 0.5% chance of getting cancer, and you start panicking, right? Because you don't understand the risk. For a doctor, that's nothing. It's why are you panicking? It's nothing, right? So this is a known versus an unknown risk. An unknown risk is much worse in my mind than a known risk, because I can deal with a known risk. I know what the possibilities are, what can happen and what will not happen. It is a risk, but it is not going to happen. And so that part leads to a public resistance to say, we don't understand the risk. Can you tell me it is zero risk? As a scientist, I cannot say that. If I cannot say zero risk, I will be thrown out of the community. No, you will not do it here. And so what do you do as a scientist, as a technical person? What do you do when you go to a community and you're talking about risks? So what everyone in the technical world has agreed on is, let's not talk about risk. But that's not fair, right? So there is a whole thing about regulatory and public acceptance. Those two don't match often. The regulations, you can be completely compliant of every regulation, you will still not be accepted in the public eye. So this is the part which brings a challenge, because confusing and complex regulations can increase the risk. Both a risk by way of losing money through regulations that are not clear, and so what you thought you would get on tax breaks is not happening. What you thought you would get on capture cost reduction or subsidies is not happening because you misunderstood what the regulation was. Or it's causing delays, and now you're running through your capital and you're running out of money. So again, a very prime example, there are projects that have started in the case of the Department of Energy, for example. Projects are submitted in 1 year. It takes 1 year for them to grant the project, and then takes 1 more year to negotiate a signed contract. That's 2 years. If it is a company with low capital, then they've burned through all that capital in 2 years before the project even starts. And so now you're running into a cash flow problem because of delays, right? So that is a real threat for any commercial project to go through. If it's a government project, it's still a challenge because governments have to show a balanced spreadsheet at the end. Or it changes, the government changes and you leave the deficit to the new government, which comes in, then the new one says there is a deficit, let's shut this down. This part is not making money, this part is costing money. And so these are challenges that we face when we are trying to run the show. There's a capture and purity challenge. We have to have a certain amount of capture, and we need to have it in a purity standard for injection and for transport. Otherwise, we are corroding through pipelines. You can't transport that. You can't, for example, you cannot accept any sulfur, oxygen, nitrogen compounds in your contaminations, in your carbon dioxide. I should have put moisture as well, because it suddenly becomes a very corrosive gas, and now you're burning through your pipelines and you need to start changing it, or you're leaking into the atmosphere. We are planning and we are capturing carbon dioxide from industrial processes, from power plants, and directly from air. For the project that we have a choice. We have a couple, and I'll give you numbers in a minute. We have 2 cement factories, 1 steel plant in the area. The coal-fired power plant has been shut down, so that's not a source for us. And we have a planned DAC in the area, direct air capture. And so we are now deciding whether we put the DAC near the storage location, or we put it near the cement factories and pipe in the captured carbon dioxide together with the process captured carbon dioxide and have one pipeline. Right? So these are efficiency questions. These are coordination questions for all of the supply of carbon dioxide that you will be getting to your area. And these are decisions to be made. Now, these decisions are made sometimes on economics, not on efficiency. They can be made on efficiency for capture because that's what the project is. But that efficiency needs to be together with the storage part, because we will need that efficient supply of carbon dioxide to my project. My efficiency depends on having not 20 pipelines coming in, each one of them with a different contamination, then cumulatively I have too much. That means that I have to clean it up again. And so this part becomes a very big challenge to manage. It might end up with me having to say, no, we cannot accept carbon dioxide from this plant. They have enough of it, but it messes up every other supply that I have. And so we rather take less. So instead of the 1.5 million tons per year that I plan to store, I'm only storing 500,000 or 0.7. So I don't meet the capacity that I said I will meet. And now my investors start to get challenged and they start to complain because their revenue is based on how much I store, how much carbon dioxide they put away. That's the 45Q regulation in the US that pays companies for reducing their carbon dioxide. So if I now say I cannot take all of your carbon dioxide because it's not high enough purity, that is on the bank balance of that company, right? So that becomes a challenge to manage. For us, these are the suppliers, potential suppliers in the area. We have the Rio Grande, GCC Rio Grande cement plant. It produces more than 700,000 metric tons of carbon dioxide. This was in 2021, so 0.7 million metric tons in 1 year. There's Holcim Lafarge, which is much larger than the GCC plant, and so I estimate 1.5 million metric tons per year for them, just double it, right? There is the Evraz steel plant, and that emits about 0.3 million metric tons. So if I count everything up, we have more than ample carbon dioxide available to us in a small vicinity. This is a vicinity of about a radius of about 30 miles, 30 to 50 miles, not far. So if we are to transport from each one of these areas, we would need short pipelines. Now remember, this is the amount. We want to store 1 million metric tons, 1.5 million metric tons per year. You cannot truck it. It's not very practical to put it, compress it, and transport it via trucks, because then A, it's not efficient, because you will need a lot of back and forth. B, the maximum amount of maximum amount of accidents happening on the oil field is from transport, from trucks mostly. When they deliver fracking sands, when they deliver all of the materials going back and forth, when from driving around in the area, it's usually in a rural area, people are not used to that much traffic, and before you know it, there are accidents happening. That's by far the largest source of inefficiency in the oil field. If we do this by truck, we will have exactly the same thing. And we get the people against us, because they're already asking, when we drill the wells, how much traffic will we have during the day? Because they have school kids, their children are used to playing outside. They don't want to be able to curb their playing outside, right? So that becomes a challenge. Transportation is a challenge. We have to transport carbon dioxide from industrial sites to locations. Development of that infrastructure requires investment, requires a lot of investment. For us, for example, if we have 3 different locations, we need to have pipelines from each one of those locations. The steel plant is in a heavily populated area. The city has grown around it, which means we will need to transport it either a longer route or through densely populated regions. Either way, it costs. So there is a challenge in that part. Shipping, for us, it doesn't play a role, because shipping, there is no ocean here. We have a small river going through it. We're not going to use that. But there is a big plan for shipping, because the Norwegian company Equinor has set up a very large storage facility in Northern Lights, and they have built a huge container harbor to get shipments of carbon dioxide from rest of Europe, so that they can safely store it in Northern Lights, in the project there. And so this becomes a viable thing to do, but it's more challenging, more expensive, and also emits through the ship's energy consumption. The pipeline infrastructure is not very adequate, and nowhere in the world. I think construction of pipeline is from oil production areas to oil consumption areas. There is nothing that exists from carbon dioxide capture facilities to storage facilities. Those pipelines will have to be made. The best way to do that is if you have your storage right next to your capture. Not always very practical. Does happen. There are some locations that have enough land that is not built up that you can use to store on site, but not always possible. So, either inadequate or leaking carbon dioxide transport will hinder projects also. Okay. Geographic challenges. There needs to be a reliable route for pipelines or for shipping. And you need a lot of investment that is country dependent. How much incentive is the government offering? How much infrastructure is the government taking over to build? In some cases, this is the job of governments. In most cases, this is private investment. And so that gives a challenge. There is another part which is local constraints. You might not have major emitters in the area, but you have the best geology in the area. So what do? Now you have to build up your infrastructure. You have to get the logistics for transportation. You might not always have that. If you have to build up the logistics for transportation, you're looking at increased cost. And suddenly your small margin, remember the 45Q, the newer 45Q, does not provide that much incentive. So the margin is very small, the profit margin. If you're also investing in infrastructure for transportation, that eats up on your profit. Right? So it can make or break your project. We need to have a good pressure management and injection integrity. That depends on your local geology. That depends on how well do you manage how well you can manage your injection with the target that you have, with the pressure that the system can sustain. If you don't manage that, you will have either a leak or induced seismicity, mostly both. Right? If you're doing that, you're managing pressure, sometimes you can extract brine and replace it with carbon dioxide. Fine. But that brings in additional cost because now you have excess space for carbon dioxide, but you have to get rid of this brine that you've extracted. It is not usable because it's usually contaminated with various salts and with various heavy metals. You need to get rid of those, or you create another well that you use as injection well for wastewater. And then you have to have a storage site readiness, which means you characterize everything. You bring out, you drill the well, you get the core, you do all your remote measurements, and you assess the storage as well as the seal to see whether you have an adequate storage site. If this is not given, all of your investment goes down the drain. That's a challenge, right? So the investment upfront relies on how good of a job you have done to show that there is a potential, there is a good potential. The more measurements you do and the worse the prognosis becomes, now your investors start to get cold feet and they start to jump away. Or your regulations suddenly don't look as easy to meet as what you thought they would be. And so you are now looking at finding an alternative site, you're trying to save your project. You're not building your project anymore. This process of permitting and approvals, I don't know how it is, how fast the environmental authority does things here. In the US, they are severely backlogged because of the amount of money that was pumped into CCS. There are about 100 permit applications in the pipeline. The Environmental Protection Agency cannot meet the demand that is there. Now, currently there is a sort of a sad thing, because there might be a solution to that backlog because of the new government coming in, the policy drying up, and people might withdraw and say, we're not doing this anymore. And so the backlog goes away, but not because it's been approved, but because people pulled out. And that's a certain thing that is going to happen. And locally also, we need injection infrastructure to inject. We also need infrastructure to pressure up, so that we are not pressurizing while pumping. We have pre-pressurized gas that we are using to put in. So there are a lot of issues that we need to manage. Appropriate geology, we can't do anything about it. It is what it is. Pressure, we can't do much about it. We can remove some things and manage pressure balance, but there's not that much options there. And the seal is again given by the local geology. We have to be doing this as a proper selection site. We need a long-term monitoring scheme. So MMV becomes a very challenging issue, especially if you change project hands. Right? It happens very commonly in oil companies. You have a major, usually the way the life of a oil field goes is you have a big company that makes the usually it's a smaller company makes the discovery, a big company buys them out, they do the production till it is not profitable because of large overhead of big companies, so they want to sell it off. A smaller company comes in that has less overhead, they buy it, and they run the production till they are not viable anymore. A smaller company comes in, and so on. So it changes hands very often. In this case, if you have a CCS project and you change hands, whose liability is it for long-term monitoring? Whose liability is it if the company goes bankrupt, goes out of business? They were the ones who started this long-term storage. Whose responsibility it is if there is a leak? Who pays for it? Right? So these are real issues that need to be solved. There are some countries that are saying, that's okay. What we will do is we will have a fund that you need to pay into right up front. Every time you do a storage project, you automatically put away this amount of money, and that will pay for any leak in the whole country. We don't have a very good accountability system right now. Who says how much have you stored and how much have you effectively captured, right? So this is the part where accounting comes in, accounting for your gas metering, your gas injection, everything that you're putting in, and you are telling the government that you have stored that effectively. That is your accounting for carbon dioxide, because that is going to give you your tax credits. And all of this needs to be coordinated. You need to coordinate this, having each thing happen on time. It's almost like a domino effect. If this thing happens, and that thing happens, and that thing happens, one thing doesn't happen, and now suddenly your entire chain is stopped. Think of this as parallel programming, right? You have a normal program, it takes forever to run. You parallelize your code, but you don't make each branch efficient. So one part runs very quickly, And then it's waiting on this one that comes slowly, and then this one that comes even slowly, which means you have put all the effort to make a parallel program, but you have not made sure that each one of the branches that you have parallel running is equally efficient. And so you does not, in all of this, there's one thing which we all agree on, people who are in the CCS world: one successful project doesn't create acceptance. One failed project will have people doubt about the entire technology. Right? One failed project just needs one project that is leaking. Just need one blowout. Worst case scenario is a blowout that happens in a CCS site, and before we know it, we have to shut down everything because we've lost all credibility in the public eye. Right? So this becomes a major thing, and yet we need to do it, right? So now what we are trying to address is to say, what is the risk of not doing anything, and what is the risk of doing something? Now you weigh the risk. So both things have risk. You don't do something, you have a risk. You have a risk of what it is now, 2 cyclones per year in Chennai, right? We have major forest fires in Colorado. We have major snowstorms and exceptional heat and exceptional cold. Extreme weather in Colorado, which we didn't used to have. We have more than 10 days of plus 40 degrees temperature, where in the past it used to be 1 or 2 days every year. Right? Those are risks because people are not used to those high temperatures. So there is a risk of not doing anything, but there is also a risk of doing something where you might have leaks. So now we have to decide which risk are we willing to take. Okay, so how are we doing with time? I think I have only 2-3 slides. We can do solid transport tomorrow, but let's just look at the pipelines today. Not pipelines, really just a little bit of what we need to do. We have a capture plant. We have a capture plant here. We put both of these through pipeline. We have a buffer storage, go into offshore transport, or we have onshore transport, and we get it to an injection site. So that's sort of what we really need. In the US, this is what we have. We have 50 million ton per year capacity to transport carbon dioxide. Existing pipeline is about 2,500 kilometers, almost 2,600. The pipeline lengths are various, right? There is 800 kilometers, 600, almost 700 kilometers. These two, or these three actually, are natural carbon dioxide reservoirs. These are not capture plants. These were put down, these pipelines were put down by various companies, mostly BP, Kinder Morgan, to transport carbon dioxide to oil field sites for enhanced oil recovery, which means that these pipelines paid for themselves because of the additional oil recovery. These are capture sites. They are shorter. They have less capacity. This one here is going to AUR field. This is from the North Dakota Gasification Company in Beulah, and it's going over to Canada. It's by far not enough even for US needs. In countries where it's not a tradition to transport by pipeline, you will need all of that infrastructure invested to put down pipelines to be able to do this. What that looks like is something like this here. And I should have reminded us again of where the major emitters are. Major emission happens out here and some over here. The storage sites are out here. This is Illinois Basin. Out here in here's Texas. Out here in Louisiana, in Colorado, in California. And we don't have very many pipelines there, right? So there will be a lot of infrastructure that will need to be constructed so that we can put in A, capture facilities, B, transport to where the storage will be. And that's the infrastructure investment that we are not so sure we will get anymore. So that's the place we are today. I don't think I have anything else. And so I will leave it at that. I think what we want to talk about tomorrow is what's the scenario for India? How many pipelines exist? What is available for transport? What mode of transport for gas do you have here? And is it enough to be transporting the amount that is captured to where it needs to go? Okay, good. Thank you.